So this is um, another seminar in the theory seminar series at NTU. Today we will continue on the topic of independent query sampling. Um, so unfortunately, the previous seminar could not be recorded. To be honest, I forgot to record it. Okay, I gave the seminar without turning on the recording. Uh, so um, so I understand perhaps um, you missed the previous seminar. So I'll try to do something to give you a quick idea of what we talked about last time. Okay. Um, so I hope you still remember what IQS is. Okay, so I guess maybe it's been a while since we talked about IQS because we talked about IQS some time ago, and in the past few seminars I have been talking about it, but I guess if you have missed those seminars, perhaps it would be a bit difficult for you to understand today's seminar directly. So I think it will be um, it will make sense to give you some background information again, or also just to brush up your memory. Um, well, you still remember traditional range reporting queries, right? Range reporting, right? So this is something everybody cares about in the database area. Um, so if I have to formally define this range reporting, I will do the following. So the input has this the input is this set S. Okay, so this is a set of n integers. Okay, so you want to pre-process this set so that you can answer the following queries efficiently. So a query, right? So here I give you an interval. Let's say this is from x to y. Okay, so let's say x1 to y1. Okay, it's an interval, and you want to report everything in the data set that falls inside the interval. Okay, clear to you, right? Okay, so this is the reporting uh, problem, range reporting, right? So we know this problem can be solved using a binary search tree, for example, right? So it takes linear space and it's able to uh, answer every query in log n plus k, right? K is how many elements you want to report, correct? Okay. So this IQS, which is getting very more and more popular nowadays, basically says that this is no longer a sustainable way to interact with big data. Can you think of some possible reasons? Um, okay. Um, well, there are many reasons. Okay. So one reason is that this S is very large. It gets larger and larger. And let's say even with a traditional query queue, something that you ask every day, right? Queue doesn't change, right? This query condition doesn't change, right? So you're interested in saying, say all the people, all the transactions that have certain amounts, this amount falls into some interval that you care about, right? So this query doesn't really change. But if the data set size gets larger and larger, and then you can imagine that the query result also gets larger and larger, right? So along with big data um, come big queries, is what I mean. Okay. So big data, refer to data sets that are huge, right? But if you think about it with the same so-called selectivity, right? Selectivity, um, big data lead to big queries. Okay. And The thing is, users are not, I mean, it's very unrealistic to assume that, okay, users will just sit there and wait for the entire query result to be reported, right? Because when you have big queries, and then it takes long time for people to wait for the result, right? So this is, like I said, not a very sustainable way to do the query processing, okay? And in many situations, you don't really need to report the full result. Let me give you some other examples, right? So let's say you go to, I mean, you are designing some online applications, right? So you have a query condition, and this query condition retrieves, let's say, 10,000 points, 10,000 elements, okay? But the thing is, you can only display 10 elements. You see what I mean? 10 elements on the browser, inside the browser of this user, right? So think about, for example, hotels.com, right? So I want to find all the hotels, within this price range, right? So there are many of them, right? But you can only display 10, right? And suppose all the other conditions are identical, these hotels, they are equally good, they're equally popular, et cetera, et cetera. Now, which 10 are you going to display? You see what I'm saying, right? So this is another reason why retrieving the entire result is one way to deal with it, but not the only way, and probably not the best way to deal with it. Okay. So the IQS, the idea behind IQS is saying that, okay, if this is not sustainable, then what would be a sustainable way to deal with this BigQuery situation, right? So this IQS says, okay, now every reporting version comes with an IQS version. So let me repeat, right? Every reporting, now this is just one reporting query that people have studied before, right? In the data structure domain, right? So every such kind of reporting query has its IQS version. So by the way, what would be an alternative reporting problem, for example? This is one-dimensional, right? You think about it, this is one-dimensional. Think about two-dimensional, the two-dimensional counterpart, right? So there you have a bunch of points, say restaurants in Singapore, right? And then what would be a query? A query would be a region. You see what I mean? Would be a region, right? And then you can say, okay, find me all the restaurants, in this region, right? So this would be a two-dimensional. So that would be a reporting query as well, right? So as I said, every reporting query has an IQS counterpart, right? So this IQS counterpart, takes a conventional um, predicate like this one as one parameter. But it also takes another parameter. So this is like how many results you want. Okay. Okay. You want at least one result, right? S. So what you want to do is you want to report a sample set. Okay. So I'm going to talk about weighted sample set later, right? But anyway, a sample set of S over Q. Okay. And this sample set has size. Okay. Size S. So I mean, okay. So basically it says, okay, the query result is too big. And we cannot afford, and we do not need, probably, we do not need all the elements in the entire result, okay? And all we need is just some good sample. It has to be reasonable sampling, right? You cannot say I return arbitrary S elements here. S, by the way, of course, is way smaller than the size of the entire result, right? So what you want to do is you say, okay, I want just 10, for example. But these 10 will have to be genuinely randomly sampled from the entire result. Okay, so that's the deal here, right? Okay, so this is the IQS version of the traditional reporting problem, right? So I'm going to pause here a little bit to see if you have questions. So basically, I'm filling in the background because otherwise it would be impossible to go into today's material. Okay, so I will pause here to see if you have any questions about this, about what is this IQS? So IQS is independent query sampling, by the way. Independent query sampling. Okay. Okay. All right. Does this? Yeah. Go ahead.
As a single obvious difference between these two.
Uh huh. Uh huh. So can you explain to me the definition of IQS? What is S here?
Yeah, I'm not right. Just the
Size constraint, well, more than that. It's how many samples you want. Okay, how many samples, right? So let's say S is 1. What should you return? So if S is 1, you want to return just one element, but it cannot be an arbitrary element. It has to be a random element. You see what I mean, right? So think about machine learning situations today, right? So you want to train a model, right? But you know today they are very selective, right? Because they already have a large model. They would like to fine tune certain parameters in the model, right? So what do? You don't really take the entire training corpus to retrain the whole model because that's overkill, right? So you want to find only samples from the relevant part of the database, is what I'm saying, to train the model, right? But the thing is, you don't really need the whole relevant part because the whole relevant part could be very, very large, right? So if you have experience with training, oftentimes it suffices to use a much smaller random, but it has to be a random subset, right? Because if you say, okay, you take arbitrary subset, then you might suffer from this bias issue, right? So that's the background here, right? So you give a condition, you say, you know what, I'm not interested in the entire result. That's an overkill for me, but you have to make sure this is sampling, right? And another example would be like hotels.com, right? So let's say you want to go to Bali for some vacation, okay? So you want to search for the price, let's say between 100 and 200 per night, okay? Maybe there will be 100 hotels satisfying your condition, right? So in reality, they have some sort of ranking mechanism, but depending on, popularity and that kind of stuff, right? But let's say all those conditions are identical for the 100. I mean, at some point, you will have some ties that you cannot break, right? And then you are facing the following question, right? You can only display 10 hotels, in the browser of the user. Now, which 10, right? You cannot really fairly say, okay, I display your hotel, but I do not display another hotel. I mean, what would be the ground for that, right? That would not be a very reasonable way to do this business, right? However, if you think about random sampling, and then this is saying, you know what, S is 10 here, all right, and there are 100 hotels satisfying the condition. And now I'm just gonna randomly, I mean, genuinely random, right? No one should complain, right? So I would take 10 random samples from all these hotels and display them for you, right? And then that would achieve a strong sense of fairness, right? Okay. Actually, there are many other situations. For example, today we're talking about being politically correct. You see what I'm saying? You cannot really display certain you will have to sort of like justify how representative your result is if you choose to present only a subset of the result. You see what I'm saying? So how would you be able to justify that? You see what I'm saying? I think one easy way to justify it is, this is just a random sample, and it's guaranteed to be a random sample, right? Anyway, if you think about the essence of the problem, as I said, right? So big data, right, lead to big queries, right? Because the query condition, let's say, remains the same for a fixed query, right? It's easy to imagine that when the data set size continues to grow, right? And then the query size also becomes larger and larger, right? If you think about it in the long run, this is not so sustainable because in the past, when the query result was small, and then people would be able to sit in front of the computer for 2 minutes to get all the entire result, right? But now you have to sit in front of the computer for 20 minutes. But that will be the game changer. So I mean, that's going to change the way that people interact with the database. Actually, that's already happening, right? So if you think about e-commerce, right? Think about all the logs generated, right? If you say, okay, find me all the transactions between 1 o'clock and 2 o'clock, you will find 2 million of them, right? And it's simply not possible to just retrieve all the 2 million, but you don't really need 2 million. So what I'm saying, all of a sudden, I mean, oftentimes you only need to sort of like extract a sample, and then you do some analysis to see, okay, how many of them are, let's say, good transactions, bad transactions. When it comes to such kind of statistical analysis, you don't really need the whole population, right? Say if you want to do the survey on, you want to do you want to do a survey on how many people support Donald Trump, how many people support the other candidate. You don't really call everybody, right? So you basically call about 1,000 people, right? So that will give you very high confidence intervals, right? So all these reasons are behind this IQS. Okay, so it's very important that you achieve independence, right? I here stands for independence, right? So what this independence basically says that every time I give you a query, even the same query, x1, x2, right? You are supposed to draw the samples from scratch. You're supposed to give me fresh sample. You cannot say, hey, you know what? These 10 samples were returned for the last query. And since your query is precisely the same, I'm going to give you these 10 samples again. Now, this is beating the purpose. You see what I'm saying, right? So conceptually, you should achieve the following. For every query, for every query condition, conceptually, right? You can imagine you first compute the entire result, and then from the result, you return as random samples. So you have to do it. You have to guarantee that the effect of what you do is the same as this conceptual approach. Okay. All right. So I'm going to pause here again to see if you have any questions. Any questions you'd like to ask before we go on? Because you won't be interested in the technical stuff unless you are convinced that this is something worth listening to. Do you have any questions about the problem definition? No? Okay. All right. So let's come back to the sample set. All right. So still I'm filling in the background. All right? Today's seminar will probably have to overrun because I've spent some time on the background. So this sample set here requires further clarification. Okay. Because when we talk about sampling, there are many sampling schemes. Okay. One easy scheme would be saying, you want to draw one sample and just, draw each element from the query result uniformly at random. Okay, so every element gets the same probability of being sampled, right? So that would be a simple case. So we tackle a more difficult case. Okay, so in this case, we say, this is weighted sampling. All right, weighted sample. Now think about hotels.com, right? So that would be an excellent example. Hotel.com. Those hotels, they actually pay different money. Probably, I don't know for sure, right? But I heard some of them they actually pay so that they can get ranked higher, right? And there are also other factors as well, right? So some hotels they are more popular, and so I would say it makes sense for hotels.com to display them higher up, right? Okay, so there are factors like this. So you can think about it like, okay, so if you want to draw a sample, not every single hotel should be drawn with the same probability, right? So its probability should be affected by its weight. You see what I mean? If your weight is so huge, let's say you account for 99.9% of the weight, and then you should be drawn with 99.9% probability, right? But if your weight is very small, you still have some probability to be drawn. It's just that it's not as large as some other guys, right? But it's fair in that sense. You see what I'm saying? Okay, good, excellent. So so this is actually the version of the problem that we have been tackling in the past few weeks. So today I will give a self-contained definition before I continue. Okay. So here, for every element in the set S, okay, for each Y in S. Okay, so this Y is an element, okay, in the data set S. There is a weight, okay, so this is WE, and this weight is something positive, okay, so this is a weight, okay. So we will not be concerned with how you compute this weight, except that, somebody has already computed this weight, okay. And once the weight has been decided, and then you can define what it means by a weighted sample, right? So let's say here, this set here, let's call it SQ. Okay, so this subscript Q here reminds you that this is an intersection. Okay, so what you can, so what you do is the following, right? So when we say we want to draw a weighted sample from SQ, what do we mean by that? Okay, when we say we want to draw a weighted sample from SQ, so what we mean is, we want to return a random variable, say x. Okay, so this x, such that this probability for x being y, and here this y is any element in the query result, right? Right. So this will have to be proportional to the weight of this element. So I mean, let's say your weight is 99, my weight is 1, and we are the only two elements in the result. And then you should be drawn with 99% probability, and me would be 1%, right? So how do we define this formula? So this will be the fraction WE over the summation of all the elements, the weights of all the elements in the query result. So that is the probability. Makes sense, right? Okay, so you see this is the formal definition. So that would be one weighted sample. Okay, so now I say I want S weighted samples. Okay, so how would you be able to solve this query? Okay, so once again, if you compute the result SQ completely, and then you can easily do this. Okay, so for example, if you still remember the alias structure, you can build an alias structure after you have computed this SQ, and then you can draw samples, right? But that would defeat the purpose. You see what I mean? The main objective here is saying, okay, since you only want S, right, and this S could be way smaller than this SQ, right? Is it possible to do much, much faster than first computing this SQ? Okay. All right, so that is the problem. Okay, good. Very nice. Excellent. So we have been talking about this for several weeks now. So if you look back at the lecture notes, you know that currently we're able to solve the problem with a structure with linear space. By the way, n is the size of the set here. So you can see, right, the size of the data set there. And you're able to answer any query in log n plus s time. Okay, so this is what we're able to achieve. So you can see that this is plus, right? So this is sort of like a replacement of the conventional log n plus k, right? So this is plus s, so s is much smaller than k. Okay, so that's the thing. Okay. All right. So why are we talking about this today? All right. So there's something very important we talked about last week. Okay. So as you can see, this is just talking about one particular reporting query, right? So this is 1D range reporting. Okay. I mentioned earlier that there are many other reporting queries as well. For example, if you talk about two-dimensional, three-dimensional, four-dimensional, so you have all these queries, but it doesn't have to be orthogonal, right? You could, for example, you could have a disk. You see what I mean? A sphere, right? You would say, yes, please.
You mentioned about the Elias method. If I chose to use that method, then how bad can it be if I just repeatedly sample that?
Yeah, sure. So you first retrieve the entire set first, right? Okay, so and then it depends on the size of the set, right? Right. So if the size of the set is k, right, and then it will be log n plus k to retrieve the entire SQ, correct? And then after that, things go fast, right? And then you can spend k time. I said k is the size of SQ, right? You can spend k time to build an alias structure on SQ. And then after that, you can draw as many samples as you want, right?
Like log k plus s
plus. Log n plus k.
Log n plus s plus.
Log n plus k plus s, correct. Yeah. So we I mean, this S is typically way less than K, right? Okay, so it will be essentially log n plus K, right?
Yeah.
Okay, so basically it depends on the comparison between S and K, right? So the motivation here is that you have big queries. You see what I mean? So K is huge. Think about K being a million,
Mhm.
but S is 10, right? So that is the difference we're talking about here.
Uh,
Yes, go ahead.
Question
Yeah.
about the scenario you just
Yeah, yeah, yeah.
mentioned.
Mhm.
In this scenario, we need to build an alias structure once we retrieve the K result.
Correct. Yeah.
But we need to increase this complexity into the whole time complexity.
Of course, but it's a linear time to build an alias structure.
Yeah.
Okay. Linear time. So you build this alias structure on SQ only.
Yes.
Okay. So if you have K elements, how much time do you need to build an alias structure?
Long.
It's K, big O of K. Okay, just linear. Yeah, big O of K. Okay, so it's a linear time constructible. Okay, so let's calculate the time more carefully, right? So you use a binary search tree, and then you can get SQ in log n plus K time, no problem, right? Okay, so that's the first step, right? And then I have SQ, correct? Mm-hmm. Now I build the alias structure on SQ. I build the alias structure on SQ. Fine? Okay, so that takes another K time, right? So there's log n plus K, correct? Okay, good. And then I have already got the alias structure. Alias structure basically says after you have built the structure, and then you can get a weighted sample in just constant time. So if you want S weighted samples, and then you spend another S time to get S samples, right? So overall, the performance is going to be log n plus K plus S, correct? Did I answer your question?
Yes.
Yeah, good. So that's essentially log n plus K, right? Because S is way less than K, right? Okay, good. On the other hand, we can do this. Okay, all right. Okay, great. So I think now we're in the context. Okay, yeah. So I was saying today we're going to talk about this tree sampling. So I'm going to define this tree sampling, and then I will remind you why we're talking about this. Okay. So this tree sampling says the following. I have a tree for you. You know, this is an arbitrary tree. Sorry. Yeah, this is an arbitrary tree. Let's say it doesn't have to be binary. You know, it doesn't have to be balanced either. You know, it's a really arbitrary tree. Okay. All right, something like this, right? And you can see leaves here, correct? Okay, we only want to sample the leaves. All right, we're not interested in internal nodes. All right. However, you have conditions. Okay, so what you can specify is, you know, I will choose a node, typically an internal node, but it can also be a leaf. It doesn't matter, right? But if I choose a node here, I'm interested in only the leaves under the node. Okay, we're not interested in these two leaves, for example, right? So we're interested in only these four leaves under the node. Okay, and the goal is to do a weighted sample to extract a weighted sample from the leaves underneath this node. Okay. So I mentioned the word weighted sample, right? So by now, I think it should be clear what it means by weighted sample, right? So in this case, every leaf will carry a weight, right? So there's weight here, WE, right? Except that, you know, every leaf carries a weight. So not all the leaves are equal, okay? So every weight carries a leaf, right? So when you have when you have chosen an internal node, you can imagine, you know, the query result would be the set of leaves underneath the node, correct? Okay. And then from the query result, you want to extract one sample, right? So that is called a tree sampling problem. Okay, good. Well, here is something we talked about last time. So last time we show a reduction from tree sampling to this IQS version of the range reporting problem, okay? So if you have n leaves inside this tree, okay, so you are able to do linear space. You are able to use an IQS version of this range reporting structure to solve this tree sampling problem. Okay, so there is a reduction based on DFS. Today, I'm not going to talk about that again, but if you are interested in knowing how this thing can be done, I'm afraid you will have to read the lecture notes. Okay. There was no video because once again, I forgot to record the seminar last time. Anyway, so this will give you one solution. All right. The solution is not bad at all, right? So linear space, but log n plus s. Okay. So in this case, for example, I choose the red nail here. I say, okay, give me 2 samples, and then it's going to be log n plus 2. All right, good. And it's a weighted sampling. Very nice. So today we will improve this. All right, today we want to do linear space and then log n plus s. 2 logs, okay, log n, log of log n, all right? So this is a little bit unusual, right? You don't really see this all the time in sigma, right? It's a log n, right, plus s, right? Okay, so let's see how to achieve the purpose. In fact, after today, you are actually able to do log n. Okay, once you understand how to do log n, you can actually do log n, right? So basically, this term will get smaller and smaller. All right, the trade-off is the space consumption is going to increase, but still it's linear, right? So but the hidden constant is going to be larger, right? Now, before I talk about the technical details, let's first understand why we want to do this. Why is tree sampling occupying so much attention from our seminars? Okay, so this is there's one very important reason why people are interested in tree sampling. Okay, last time we talked about a generic reduction that converts many reporting structures to their IQS counterparts. Okay, so for example, you could convert a B tree to its IQS counterpart. Okay, so even if you missed all the previous seminars, you can take it for granted, right? So if you have a B tree that can do log n plus k, using tree sampling, you immediately get an IQS version of the structure. However, the query time will become log square plus s. Log square. You see, the B tree is log n plus k, right? But at this moment, if you apply the reduction that I talked about last time, and then the query time you get will be log square. You know, there's a log n deterioration here. And that deterioration actually comes from this log n plus s. Because, currently we can only do tree sampling in log n plus s. So imagine if you were able to do tree sampling in 1 plus s, and then there will be no deterioration at all. You see what I mean? And therefore, the efficiency of the reduction that I talked about last time, in simple words, right, uses tree sampling as a black box. If you can solve tree sampling better, and then the reduction is more powerful. You see what I'm saying? All right. So today, we'll reduce this log n to log n, and immediately from the B tree, for range reporting, you will be able to get an IQS version of the B tree with query time log n times log n plus s. Now here, the deterioration factor will be just log n, okay? This can actually be reduced even further, all right? So I'm not going to talk about it today, but I'm just telling you that this can be done in 1 plus s. Today, we will not be talking about how to do 1 plus s. We'll be talking about how to do log n plus s. Okay, but as a short message, if you want to do 1 plus s, the first step is to do log n plus s, and then you apply the so-called tabulation technique. This is not a technique we'll talk about today. Okay, it's a theoretical technique, but it's not very efficient in practice. Okay, but we'll talk about how to do log n plus n, log n plus s, and that's very practical. Go ahead. Yes.
Well, what we are going to talk about is something related to finding the cover if it's sampling.
Finding the cover, no. The short answer is no. Not today. Okay. However, finding the cover is one key step in implementing the reduction that I mentioned. Okay, so in general, if you have a reporting structure like a B tree, okay, so there's a notion of cover there, okay, and after you have identified a so-called cover, and then you will perform IQS, the IQS version, by resorting to tree sampling. Okay, so what you just said is actually stuff in the last week's seminar. Yeah. Okay. Do you have another question?
Just a continuing question about
Yeah.
cover. Does cover usually contribute to most of the time in the tree sample and finding the cover?
Yeah, you're absolutely right. So I think you are still talking about the reduction, right? So I can give you more ideas about that reduction, right? So the reduction basically says you have a query. The query results is like this, right? So by cover, we're saying, okay, we are able to find some subtrees. Okay, you see a B tree is a tree, right? So we're able to find a small number of subtrees. So these subtrees will together occupy the query. Will give you the query result. So that's the meaning of a cover. Okay, good. More specifically, in the B tree, the number of subtrees that you can find is no more than log n. Okay, big O of log n. Okay, so and then you are able to imagine that you will be solving log n tree sampling problems. Log n tree sampling problems. Okay, so that's how the reduction works. Okay, but since each tree sampling will give you another log n factor, right? And you have to solve log n of them, so that's how you get loss square, right? But if we're able to completely remove this log n, let's say in each tree sampling you do just 1 plus s, and then if you are able to solve it, and then since you need to solve log n tree sampling, and each tree sampling gives you only one, right? And then overall you will get log n plus s, and then there will be no deterioration from the B tree to its IQS version. Okay, so that's how things work. Yeah, good. Okay, very nice. Okay, nice. Okay. So today my goal is to give you a tree sampling data structure that uses linear space and log n plus s. Okay, good. All right. So as mentioned, last time I provided a reduction, right? So I said if you want to solve tree sampling, all you have to do is to solve a special version of this IQS version of 1D range reporting. Okay, so what do I mean by this special version? Now I am giving you a self-contained definition here. Okay, so this is special version of IQS. The IQS version of 1D range reporting. Okay. So once again, you've got a set. Okay, so this is set is a set of sorry about that. A set of n intervals, say in the domain, let's say n. Okay, actually, you know what? A big O of n. Let's say you know what? Let's say we have a set of intervals in this domain n. Okay. So in other words, you can think about the elements are just 1, 2, all the way to n. Okay. Oh, by the way, what is this notation here? This means the set of integers from 1, containing 1, 2, all the way to n. Okay. So if I say something like this, you can imagine, that the integers are very trivial. The elements in the set are very trivial. They are simply 1, 2 to n. Okay. So suffice us to look at such a very special set. Okay. But each element, as I said, right, each element E in S has a weight, right? Has a weight WE, right? So this is something positive. Okay, good. So now a query contains an interval, let's say x1, x2. That's fine, right? Okay, so let's say this is Q, and you want to say we have this Q here. And also you have this S. So this S tells you how many samples you want to get, right? So now you want to returns as weighted samples. from this SQ. So this SQ is defined as the intersection of S and Q. Okay, so this is the problem, right? So the key difference between this special version and the generic version is that in this version, every element, I mean, the data sets are very regular. So it goes from 1 to n, right? So it suffices to solve this problem. If you want to do tree sampling, you want to solve this problem, okay? And this is the problem that we can solve, in log n plus s. Actually, we can solve the problem in 1 plus s. Okay, so today we'll do log. Okay, good. So before continuing, I have to mention a very famous result in computer science. Okay, so this is called LCA. This is something orthogonal to what I'm about to solve. All right, so this is called LCA. LCA stands for lowest common ancestor. Okay. So here you have an arbitrary tree. This tree is not really the tree in tree sampling, right? So I'm really saying, this is an arbitrary tree. Okay, it doesn't really matter. It's an arbitrary tree. Okay. So LCA says you have two nodes. Let's say you get this node and I don't know this node. Okay, U and V. Okay. What is the lowest common ancestor of this U and V? This is the node here. This is the node, right? Okay. So this is clear, right? What it means by LCA. Good. Now the LCA problem says the following: you have a tree. Now I emphasize this is not really a tree in tree sampling. This is an arbitrary tree, right? So you want to pre-process this tree so that I give you any two nodes. You can always find me the LCA in constant time. Now this is something important. Okay, this is something important. All right, and you are able to do this. This is a well-known result in computer science. Okay, so you are able to do linear space linear to the number of nodes in the tree. Okay, and I give you any U and V, you are able to find the LCA in constant time. Okay, so you can take it for granted. Yeah.
You mean do some pre-processing?
Yeah, definitely. It's a data structure problem. Okay, you do pre-processing, right? Mm-hmm.
So the complexity of the pre-processing is
Linear
in the size of log.
Yes. So it's a perfect data structure.
Related to number of layouts, the tree.
Levels.
I was asked edges because and now it's
Edges.
Yeah.
I know. Yeah. So the number of nodes and the number of edges, they are at the same level. Okay. All right. So that's LCA. Is that right? Okay. Now for our problem, we will need only a special LCA. So for our problem, the tree that we'll be interested in, for LCA will be a perfect binary tree. Okay, a perfect binary. You know what a perfect binary tree is, right? And I said this is a perfect binary tree with 8 leaves. Okay, as you can see, all the leaves are at the same level and all the levels are full, right? So this is perfect binary tree. And also, whenever I ask you U and V, they are always leaves. Okay, so for example, these two guys, right? So in this case, I ask you what is the LCA, and then you should give me the root, correct? But if this is not what I'm asking, let's say if these two leaves are U and V, and then LCA will be this guy, right? So if I say, all right, so on a perfect binary tree, I want you to create a data structure so that whenever I give you two leaves, you find me the LCA in constant time. This will be a much easier problem. Okay, so I will not go into the details. I have a description in my lecture notes, but the idea is you basically know where your LCA is, right? So as long as you know the positions of the leaves, right? Yeah, so you can basically figure out without even looking at the tree, right? You can figure out where your LCA must be, and then what remains is to be able to store these LCAs in a way that you can do hashing on. You see what I mean? So that's sort of the idea. Okay, good. So this is just to help you believe that this is possible, because later I will require an LCA structure. Okay, so basically this LCA structure is there to to remove the necessity of doing any searching. You see what I mean? Okay. Otherwise, I would have to sort of like descend from the root and look for the LCA, and that's going to take log n time, the worst case, right? So this is the reason why we'll be using LCA. LCA, by the way, LCA structures are very practical. There are so many LCA structures out there. Okay, so it's very, very practical, right? You can actually really save this log n time in practice. Okay, awesome. Very nice. So now let's continue. Okay, so by the way, today I'll have to overrun. I think I'll probably need another 30 minutes. Okay. All right, now let's look at the original problem. Okay, so before I tell you how to do log n plus s, let's review a structure. Review a structure of space n log n and query time log n plus s. Well, this is a structure that I talked about several seminars back. Okay, so but I guess it would be too much to ask to. I mean, if I say you have to read all my lecture notes before coming to the next seminar, that would be too much to ask, right? So I guess it would be useful to quickly talk about how to do this n log n, how to achieve these guarantees. Okay, space n log n and query log n plus s. Okay. So in order to achieve this purpose, you can do the following, right? So remember, you have the data set, right? The data set, goes from 1 to n, correct? So you want to build a binary search tree on these n elements. You see what I mean? So let me show you a very simple example. If these are the data elements, and then what would you put at the internal levels here? So there are many versions, right? And many versions work. Okay, so my version for today would be this, right? So for every internal node, for example, this is the internal node, right? So you look at the right subtree, and you put the smallest key, right? Put the smallest key here. Well, basically, this smallest key basically says if you are looking for something at least 6, then you should go right. Right, so that's why it's the smallest key, right? If you want to look for something less than 6, then you should go left, right? So that's the simple rationale, right? So if I stick to this principle, this policy, and then the keys are, I'm showing you the keys determined, right? So you see that will be the binary search tree, correct? Okay, good. Now, what I want you to do is this, right? I want you to, for every node here, for every node in the tree, right? So I'm circling, this is 7, but it doesn't have to be 7, right? So for every node in the tree, I want you to look at all the leaves in the subtree, right? Ask yourself, okay, what are the data elements that appear in the subtree, right? So this will be 5, 6, 7, 8, correct? So next, I'm going to use this notation. If this node is U, right? So I'm gonna say SU to refer to the elements that are inside the subtree. Is that all right? Okay, so this S is 1 to 8, right? But I have a condition here, right? So this U, right? So basically it says, okay, what are the keys that are inside the subtree, right? So for example, if I say, okay, U is 3, and then SU would be 1 to 4. Okay, if I say U is this leaf node 4, I'm making a video, okay? So if I say, okay, this is the leaf I'm talking about, right? So, and then SU will be just 4 itself, right? Okay, good, nice. Now, what I want you to do is this, right? So for every node U in the tree, I want you to build an alias structure on SU. Now remember, these are the leaves, right? 5, 6, 7, 8, they are the leaves here, right? And they are weighted, right? Each one of them carries a weight, right? So what you want to do is to build an alias structure for this U and store the alias structure along with U. Okay, you can do that, right? Okay. So if you do this, what is the total amount of space? The amount of space is n log n. Why n log n? Now think about it, right? So I build an alias structure at every single leaf, right? So the structure for this leaf 1 takes 1 space. the structure for this leaf 2 takes 1 space, right? Etc. Etc. So the total space that you span on the alias structures associated with the leaf nodes is n, correct? Now let's go one level up, right? So for this 2, internal node 2, right? The space is big O of 2, correct? Because there are 2 elements inside it, right? So for 4, it's big O of 2, right? Etc. Etc. So if you add up the space of this level, it's once again n, correct? Okay, and same goes to every level. Yeah, you have log n as the height, right? And therefore it's n times log n, right? So that's the total memory space. So that's the space consumption. Okay. Now if I give you a query, you can actually utilize these alias structures to extract samples without computing the whole result. Okay, let's see how, right? So let's say, what if I say, okay, the query goes from, let's say, 1 to 8. Okay, sort of like the largest query possible, right? So if this is the case, I think there was a question about cover, right? So you can cover the entire result using only 4 nodes. Actually, more than 4 nodes. I'm sorry about that. Let's say 6 nodes. Okay. 6 nodes. You would say, okay, you can cover the entire result using the root. That will also be correct. Okay, just it's just that there's more than one way to do so. Okay, but the way that I'm showing you is more representative in the sense that this is something that we will use again. Okay. Anyway, so if you look at these nodes, right? So these nodes, they form a cover. What do I mean by forming a cover? Look, their subtrees are disjoint, correct? Their subtrees are disjoint. And also their subtrees together, they cover the entire query result, correct? Okay. And the reason why I'm showing you these nodes, these 6 nodes, rather than just one root, if you choose the root, you can also say the same thing, right? Its subtree also covers the entire query result. However, I'm showing you to convince you that you can actually find big O of log n nodes in the cover. This is called a canonical cover, actually. Why log n? Because think about it, right? So you go from 5 to the left-hand side, right? And every time you make a left turn, for example, at 3 here, right? You make a left turn, right? So what can you say about the right subtree here? You know that the entire right subtree falls within the query range, right? So that's why it suffices to take the sibling of these 2, right? You make a left turn and then you take the right sibling, right? You make a left turn, you take the right sibling, right? So that's how these nodes are computed, right? So it's very intuitive. But this is symmetric, you see what I mean? Okay, symmetric, so you take these nodes, right? So let's say this time I give you another example. Same algorithm still works. Okay, so let's say now this time, the query goes from 1 to 4, right? And then which would be the canonical nodes according to the policy, according to the algorithm that I explained? Well, look, so you see the 2 search paths diverge from here. This is the lowest common ancestor, right? LCA, right? So you start from the LCA and you walk to the left and you walk to the right, right? So you see these 2 paths, they diverge at the LCA. That's basically the definition of LCA, correct? So every time you look at the left path here, right? Every time you make a left path, since you have descended from the LCA, right? So what can you say about the right subtree here? Same as before, right? The right subtree will have to fall within the query, correct? So that's why I just grab the whole of it, right? Same here, right? So if I say, what are the canonical nodes? And then you should tell me, well, these are the canonical nodes. You see what I mean? So just to convince you that you can do this always in log n time, right? You can collect log n nodes to form a cover. Good. So if this is the case, how would you do log n plus s? Is it trivial now, right? So think about it, right? So if I want to get just one sample, what would I do? So I would first decide, okay, at the, from these 4 nodes, right? From these 4 nodes, which subtree am I going to sample? From which subtree I'm going to sample? You see what I mean? You know what? Let's look at the previous example because there you have Okay, I want to make sure you understand this before I continue. Feel free to ask questions there. Okay, so here, what are the canonical nodes? These are the canonical nodes, correct? These are the canonical nodes, right? Okay. So that's the query, right? 1 to 8, right? So in this case, I would first sample from these 6 red nodes. If I want to take 100 samples, I would do a two-step approach. I'll do a two-step approach, right? So first, I will look at these nodes only. I will do weighted sampling over these 6 nodes. I wonder if this makes sense to you. Okay, so on every node, I have a what? I have a set, correct? Okay, so I have a set with respect to the elements inside the subtree, correct? Okay, good. So I want you to think about every node carrying a weight. So for example, the weight of 4 will be the sum of the weights of 3 and 4 in the leaves. Not in the leaves, sorry. The leaves 3 and 4 inside the subtree. Okay, you see what I mean? Now you have 6 weights here, correct? Okay, so I want you to first choose among these 6 nodes. You see what I mean? Okay, you first do weighted sampling over these 6 nodes. You see what I mean? Okay, and then after that, in the second step, let's say in the first step you have chosen this internal node res6 here, right? And then in the second step, you would do tree sampling from its subtree. You see what I mean? Okay, so this is the two-step approach. Okay, I give you some time to chew on this. And if you have any questions, you can ask me if you're not convinced that this works. Okay, think about the algorithm again, right? So once again, the algorithm is this, right? You find the canonical nodes, right? The cover.
What's the sign of that?
Log n, right? Log n, right? So you have log n, right? So what you want to do is you want to build an alias structure over these log n nodes, right? Using their weights, right? So this takes only log n time, correct? And then when you want to draw a sample, you first draw from these 6 nodes first. But this is a weighted sampling. You see what I mean? Every node carries different weights. Okay. All right. Say if the first step says, okay, you just sample this 4, this red node 4. And then my question for you now is, what will be the second step? I mean, the second step is like, okay, I already know I will have to draw from this group, right? So now you just go ahead and draw something from this group, right? So that is the idea, right? But the most important thing is there are 2 important things here. You see, this is first of all pre-sampling. This is tree sampling. The second thing is that you have already got a weighted. You have already built an alias structure for 4.
What's that?
Alias structure, right? Alias structure, right? Alias. Okay, so that's something we talked about.
I missed that.
Yeah, you missed that. Okay, so basically the alias structure says if you have a set, no condition, you want to draw weighted samples from the set. Okay, so you can build this structure, and the structure uses only linear space, and it's able to give you time, constant time sampling time. Okay, you got a question?
Yeah, I forgot it.
Okay. All right. So anyway, so this SU basically says you create an alias structure, okay, here with respect to these 2 guys. Okay.
Yeah. The question is the weight to be normalized, like it is subtree 1 or does it not need to subtree 1?
When you say where, you mean weights of what? Weights of these 6 nodes, right?
Yeah.
Yeah, the alias structure takes care of that, right? So think about the problem solved by the alias structure, right? It's called the weighted sampling problem, defined as follows, right? So every element has a weight, right? So and then you give all these weights to the alias structure,
Yeah,
right?
the weight is the weight need to be normalized, or they will normalize itself. The alias problem will normalize itself.
So the short answer is yes, it will sort of normalize itself, right? But I would like you to think about from the problem definition, because in the problem definition, it's already taken care of. Look, so the problem definition of weighted sampling says every element has a weight. And then the probability that an element is drawn is equivalent to its own weight over the total weight of all the elements. So it's taken off right here. You see what I mean? Okay, so when I say you build an alias structure over these 6 elements, right? And then the probability that each element gets sampled is proportional to its weight, right? Precisely the probability is its own weight divided by the sum of all the weights of the elements in the system.
Because the problem is defined with that, and it's we have solved the problem, so it has to.
Exactly. That's exactly how I would like you to look at it. Perfect. Yeah. Now we're together. So back to you. So this alias structure, right? So it's a really powerful structure, non-trivial. So, but the good news is, the seminar was recorded, so you can go back and take a look at it anytime. But the idea is, if you have a set, right? So let's say 3 and 4, right? You want to sample from 3 and 4. You just have to build a structure, and this takes linear time, big O of 2 here, right? And then you can draw one sample in constant time. So that's the thing. So that will give you log n plus s. Okay, are you convinced we can do log n plus s in this manner? Yeah, go ahead.
Log nodes are not unique. Right.
You are saying there's more than one way to choose canonical nodes, and you are correct. Okay, but it doesn't really matter how you choose the canonical nodes, and the same strategy always works. Okay, so for example, you could choose, let's say 3 and 7, right? So this will also form a legal cover, right? But then the algorithm's still the same, you see what I mean? And then in this case, you don't have 6, right? You have only 2, right? So what you want to do is still you want to build an alias structure now on the weights of 3 and 7, right? And then you perform the 2-step sampling.
So I think it seems that in the worst case we theory about all that.
No, you have only log n, right? So that's why I wanted to show you how to select these 6 nodes. I gave you an algorithm to choose the canonical nodes.
I believe we can choose log n.
Yeah. Then why do you want to choose n?
It seems that we can choose more than
What's that again?
it seems that we can choose more than nodes than log n.
Well, you can choose n, right, if you want, right? But that will it's unreasonable to do that, right? You want to bound you want to design a fast algorithm, not a slow algorithm, right?
Yes, but to satisfy the definition of
it satisfies the definition of cover. Okay, but canonical nodes are defined more carefully.
Something like
Yeah, canonical. Okay, we don't have to talk about canonical today, all right? But canonical basically is defined according to how I chose these 6 nodes. Okay, but if you are confused by that, it's okay, because this is something we talked about several weeks back. Okay, but what you just said is cover. Okay, is it correct to say, if you want a very large cover, you can always choose only the leaf nodes, right? So you will have as many nodes as the size of the query result, right? Okay, but that would be a very bad cover. Okay, you want to choose a good cover, right? Okay, good, very nice. So this is how you do log n plus s. Is that all right? Okay, good, very nice. Now, let's observe something. Now we start to talk about how to improve the query time to log n plus s, right? Now think about how this log n term came into place in the first place. So how this log n term, was introduced in the first place? How was it introduced in the first place? This is introduced because you, as I said, right, in the worst case, you could have log n canonical nodes in the cover, right? Still remember what we have to do during query processing? We have to build an alias structure over these 6 nodes. You still remember that? Okay, right? Okay. So this is exactly how this log n term was introduced. Okay. But what if I tell you that, hey, you know what? Let's say you choose these 6 nodes, and somebody by miracle, right, by magic, right, has already prepared a canonical node, a canonical structure for you. And the canonical structure is created only for these 6 nodes. Is what I mean? Okay, so I guess
Mhm.
I guess you were
Log in.
I guess you were confused. Okay, did you hear what I said?
Canonical node of canonical nodes. Is that what you're talking about?
No, not that fast. Okay, not that fast. What I was saying is, now, so what is the first step of the algorithm? You have these 6 nodes, right? Can you tell me what we did in this query algorithm? What we did just now?
Sample one.
No, before that, you have to build an alias structure, right? So how do you build the alias structure exactly? Because when you talk about building an alias structure, you need to have a weighted set. So where is the weighted set here?
Subtree is given for you.
Right. So when I say weighted set, I mean you have to give me 6 weights, right? So what are those 6 weights? For example, what is the weight of 4 here?
Which is sum of lists.
3 and 4, right? Exactly, right? So this is something that you can store along with this node 4, right? So that's why you have to weight it. You have to weight here, right? So and then you can collect the weighted set during query processing, right? So this is something we call on the fly, right? And then you have to spend log n time, right? Building the alias structure. So this is how we introduce this log n, right? Good. So what I'm saying is, I'm not talking about solution. What I'm just talking about a grand wish, right? What if? I mean, just what if? All right. What if someone says, hey, you can skip this log n time, building the alias structure on the fly, and the alias structure is already right here. Okay, already right here. And then you can skip the log n time. You can go directly to the second phase. And then it will be just big O of S. You see what I'm saying? There's no more log n.
How is that possible?
How is that possible? Yeah, now we're talking, right? So I said by magic, right? So that's why you're here, right? Okay. That would be very nice, right? Okay, awesome. So indeed, I'll make it possible for you. Okay, I'll make it possible for you. Okay, so next, I'm going to present a structure whose space is n log square. N log square, all right? However, the query time is 1 plus s. 1 plus s, okay? All right, n log square, okay. Now, I mentioned a grand wish, right? Grand wish, okay? Now, I'm going to, I'm going to be more realistic. So the grand wish cannot be achieved. I tell you that, okay? However, we're able to achieve something different. And this alternative wish is nearly as good as the grand wish, okay? So what I mean is this, look, I will divide the 6 nodes into 2 parts. This is one part and this is another part. Okay. So now here is one more realistic wish. Later, I'm going to change the wish later. Okay. Again. However, my first grand wish says, I wish there was a structure, alias structure over these 6 nodes, correct? I changed that wish now. So I wish, okay, so there is an alias structure on 1, 2, 4. And there's another alias structure on 6, 7, 8. Sorry, 6, 7, 8, these 3 red nodes. Okay. Well, this is not as good as my first wish, right? However, it's nearly the same. Can you see why it's nearly the same? Can you see why it's nearly the same? So if I have already given you an alias structure over 1, 2, 4, you know what that means, right? It means I get the weight of this red 1, I get the weight of this red 2, I get the weight of this red 4. I have already created an alias structure for you. for free. I give it to you as a gift. You understand that, right? And same here, right? 6, 7, 8, right? Are you able to do 1 plus s from here?
Yeah.
Okay, what would you do then
Just 7.
from these two? You have only 2. You see what I'm saying, right?
Also,
So if I say you already have an area structure on 1, 2, 4, right? So and then you can first get the total weight of 1, 2, 4, which is actually inside of the area structure, right? Because you already have the area structure, you can store one more number, right? So you can store the total weight of 1, 2, 4, correct? And same for 6, 7, 8, right? So now you can build on the fly a very small area structure, let's say conceptually, right? With just 2 elements. One is for the blue group, and the other one is for the other group, right? Okay. Of course, since you have only 2 elements, you can do other. There are easier ways to achieve the same purpose. I'm just saying, if even if you want to rely on area structure, you can think about it like now it's a constant size, right? So you can build a very small area structure just on these 2 elements, correct? And then you can sample from these 2. You see what I mean? You can sample or say, okay, I sample 1 from this size 2 area structure, right? So if it goes from the first group, and then you apply the area structure on the first group to do the second step of sampling, right? You see what I'm saying? All right, good. Awesome. So now this is the wish I aim to realize. Is that all right? Okay, good. I'm going to cut the wish a little bit further, all right? So this is my third wish. Now this time, this is truly doable, okay? So I'm going to cut it into 4 groups. Now the most important thing is that 4 is still a constant. Okay, so I'm going to cut it into these 4, all right? So if I say that for every group here, I already have an area structure pre-computed for you. Okay, in fact, as you can see, this group here, this is trivial, right? Because it contains just a single leaf. And this is also trivial, right? So basically, I will make sure that I have pre-computed an area structure for these 2 groups. Okay. Suppose I can do that, and then the rest will be easy, right? So that's why I said you could rely on the area structure, because now essentially what you have to do is to create an area structure on the fly on just 4 elements. Correct? Okay, good. Very nice. Awesome. Now this is doable. Okay, so I will show you how to create the middle groups. Okay, but because these 2 groups are trivial, right? So these are just 2 leaves, right? So I will show you how to create the middle groups, right? Okay, very nice. Okay, I will still need 15 minutes. Okay. All right, so I'm going to give you an example, and then I will illustrate this. I will use this example to illustrate, to explain what I'm going to compute in the data structure. Okay. So here you look at every leaf. Okay, let's say this is a leaf. Okay, let's call it Z. Okay, it's a leaf. It's a leaf it's a leaf of what? It's a leaf of this binary search tree. You still build a binary search tree as before, right? So we're changing the first structure, okay? But the base structure is still the same binary search tree as before, right? So now what I'm saying is you look at every leaf. For example, you look at 3, that's a leaf. You see what I mean? Okay. All right, so this is a leaf in that BST, all right? Now, this leaf has many parents, right? Has log n parents, correct? Okay, so I want you to look at each parent there. So for example, in my scenario here, let's say 3, and then I want you to look at 4. So that forms a pair. Okay, I'm gonna refer to 3 as Z. Every time you hear me say Z, so that's a leaf. Every time you hear me say U, so that's a parent. Ancestor, actually. Ancestor, not necessarily parent, okay? So for example, 4 and 3, that forms a UZ pair. 3 and 3, so this 3, right? So this red 3 and this black 3, that forms another UZ pair. Is that right? Okay, good. Now, I look at this U, I look at this Z, this U is an ancestor of Z, all right? U may not be the root, so that's why I have this edge here to remind you, U might have a parent as well. Is that all right? Okay, good. So I'm going to descend from this U down to Z. Okay, and in the meantime, I'm going to collect two nodes, S1 and S2. Okay, so in the beginning, they are empty. In the beginning, they are empty, all right? Now, every time, so I start from the child of U on this path, right? So if you look at the path from U to Z, there's only one unique path. No problem, right? So I will start from the child of this node on that path. Is that all right? Good. So each time from here, right? So if I make a left turn on the path, like here, right? And then I will include the right node, let's say, call it V1. I will include this V1 into S2. Okay, so think about S2 as sort of like right. Right. So this one means left. Okay, so as you can see here, I'm making a left turn. I'm including the right sibling. So I mean the right sibling of the guy I just descended from, right? So I put this V1 into S2. Okay. So every time I make a right turn, okay, and then the black path has a very important meaning. Okay, so the black path leads from U to Z. Okay, remember that, right? So I go down this path, and every time I make a right turn, I will include this V. I will include the left sibling into S1. Okay. So why am I using V5 here? Well, because I have an example in my lecture notes. I want to be consistent. Okay, and so on and so forth. All right. So now let's continue from here. So let's say here I make a left turn, and now here I've got V2 here. So V2 should go into S1 or S2. Huh? S1. Think again. So the answer is okay. So think about V1 and V2, right? They share something in common, correct? So every time on the black path, you branch left, and then you include the right-hand side. Okay. All right. Okay. So that's why V2 goes in here. Now continuing, now let's say here, this time I'm making a right turn, and this guy is V6. So V6 goes in there. So let's say here, make a left turn, and this is V3, and V3 goes in here. And this, I'm making a left turn again, and this is V4, so V4 goes in there. So that's okay, right? Very nice. Okay, good. You know what I'm gonna do? I will create an alias structure on S1. I will create an alias structure on S2. That's it. That's it. Okay, but of course I do it for every pair, right? Z and U. You see what I mean? Okay, so that's the modification. Okay. All right. So before I analyze the space, right? Let me give you a little test, a little question. Let's say here I've got a Z2. So let's say this is Z1, and here I've got a Z2, and say the path goes down like this. Okay, it goes down like this. So I want you to tell me what should be the S1 set for Z2 and U. Okay, you see, before when I talked about Z1, right, I said this S1 set determined by Z1 and U includes these two guys, right, V5 and V6, right? So you already know how to generate this S1 and S2, right? As S2 includes the other 4 nodes, right? So here I'm talking about this pair, right? Z2 and its ancestor U, right? So now here is a question, right? It's no longer something new, right? It's a question. So what is the set S1 determined by Z2 and U, right? S1, right? Left, right? So every time you branch right, you include the left sibling, correct? So you start from this child of U. Okay, so here you branch right, so that's why you include V7, correct? You branch right, you include VA, right? You branch right, you include V9. You see what I mean? Right. So here, of course, another relevant question is what will be the set S2, right? But I guess that should be quite trivial, right? So every time you branch left, there's something here, branch left, something here, something. You see what I mean, right? Okay, cool. All right, so that is the data structure. I have already said it clearly. I said, okay, for every such kind of pair, U and Z, right? You identify as S1, identify as S2. And for every S1, for every S2, you want to build an alias structure for it. Okay. First of all, it should be clear to you that the size of S1 and S2 is how much? Log n, right? No more than log n, right? Correct? Okay. The number of nodes.
Bounded by number of nodes.
Yeah,
is the,
height of the tree, right? Bounded by the height of, so it will be log n, correct? Okay, good. Now, what would be the total space incurred by all these alias structures, right? So that is the question I'm asking here, right? So now you look at how many pairs of Z and U. You see what I mean? Okay, so you see how many ways you can choose the leaves, and there were n leaves there, correct? Okay, so there are n ways to choose Z, correct? So for each Z, how many ways you can choose U? You have log n, big O of log n ancestors for every guy, right? So, and therefore you have n times log n, which is n log n, such kind of pairs. On every pair, as I said, right, you will need log n space, right? Big O of log n space, right? So overall, you'll be using n log n times log n, so that's n log squared space, correct? Okay, beautiful. Very nice. Now let's talk about query. Guys, you already have all the things in the data structure, so now it becomes an interesting exercise, right? So now I give you queries, X and Y, right? So still remember what a query is? Query says I give you a range, right? Okay, range, right? So still remember the range, let's say from 1 to 8, from 1 to 4, etc., right? Okay, so I give you a range. Now I say I want you to extract F weighted samples from the range, from within the range, right? So remember, in this case, the query is also in the rank space, this n, right? So the query says, okay, it's I give you 2 leaves. All right, so you don't have to search for the leaves, right? I already give you the 2 leaves, okay? So in this case, let's say the query goes from Z1 to Z2. The query goes from Z1 and Z2, right? So there's a reason why I show you this example, all right? So the query goes from Z1 and Z2, and now I want you to give me S samples in 1 plus S time. See if you can do it. Yes. All right. So still remember, right? My wish number 3, right? Now I indeed have wish number 3 now, right? So this is one group.
It should be number 2 though.
This is another group. It's number 3 because I have these 2 guys here. You see what I mean? Now think about it, right? Think about everything to see if it makes sense, right? So first of all, I want a cover. Right? So what is the cover, right? As you can see, I want all the leaves in between Z1 and Z2, correct? Okay. But you look at U. U, by the way, is the LCA of Z1 and Z2. How do I identify U? How come I'm talking about U? Yeah, that's because U is the LCA of Z1 and Z2, right? So you want to identify this LCA first, and I told you before, right? This is doable in constant time. Is that all right? So now you identify this U, correct? Okay, so now you look at this Z1U pair. You see what I'm saying, right? You look at its S2 set, right? So this is the S2 set. You understand what I'm saying? Why am I looking at S2? Now think about how I created the canonical nodes before, right? So that's why I said I wanted to show you those 6 nodes in my earlier example. Because if you understand how these 6 nodes were chosen, and then you will be able to understand how come I want to compute S1 and S2 in this manner. You see what I'm saying? So in general, how do you choose canonical nodes? You start from the LCA, because that's the place where these 2 search paths start to diverge, right? So now on the left path, every time you go left, what can you say about the right subtree? You know that since you have already diverged, right? So this is within the inner part of the query range. So that's why you know that everything inside V1 will have to fall between Z1 and Z2. You see what I'm saying? Did you buy it? Okay. Now, same here, right? Now, how come I'm not interested in V5? Because this is falling outside the query range, correct? Now here, again, I'm making left term here. So that's why, you know, the subtree of V2 must fall within the query range, right? So that's a beautiful idea if you think about it.
Yeah.
So very nice. So now I have 4 alias structures. Actually, 2 computed and 2 are trivial. You see what I mean? So this S2, this is pre-computed. And this V7, V8, V9, so that's just the S1 set of this pair determined by U and Z2, correct? Right? And Z1 and Z2 themselves, you know, they are just trivial alias structures, correct? And now you can go ahead and obtain S samples in S time. Okay, good. All right, so we're coming to the end of today's seminar. However, I do not seem to have given you what I promised before, right? Because so far, what can we do? Well, we can do n log square, n space, right? And also 1 plus s sample time, correct? But what did I promise you before? I said I would like to do linear space and then log n plus s query time. Okay, so this is what I promised, right? So left-hand side is what I have already explained today. The right-hand side is what I would like to do ultimately, correct? Okay, good. However, I don't have to talk about this because I already talked about one chunking idea 2 weeks back. Okay, now fortunately, that video was captured. Okay, you can go back and look at this chunking idea, right? So just to refresh your memory, now once you are able to do this, the n-log square space structure, so what you can do is you can divide the data set. So the data set is from 1 to n, right? So remember, right? So you can make it into several chunks, right? So each chunk includes log n square integers. You see what I mean? So you do this, and then altogether, how many intervals do you have? So this is the first interval, this is the second interval. You have n over log square.
This is
Yeah, n over log square intervals. You see what I'm saying? Okay, good. So what you want to do is you want to regard every interval as an element. You see what I mean? And this element carries a weight, all right? So the weight is equivalent to all the points, the sum of the weights of all the points inside the interval, right? So now you collect all these intervals, you have a size, you have a set of size n over log square, okay? So that's awesome because you can build this structure at the interval level. You see what I'm saying? All right. Now, to cut a very long story short, this is not going to solve the problem immediately. This will solve the problem only if the query is aligned with the endpoints of the interval. However, it's possible that the query is within the interval. You see what I mean? So that's why you still have to build something else for every interval. And that's how this log n comes into the picture. Okay. Yeah.
My last of the slides.
Yeah, so you will build a linear you will build a linear space data structure here. Okay, so I will not talk about it in the video. However, I will finish the tutorial. I will stay behind. I can talk to you how to build how to deal with the points inside each interval. Okay, all right. So this is the end of today's tutorial. Not tutorial. I'm so sorry. Seminar. Okay.